All right, picking up where we left off, we said that we were going to look at the two possibilities where we have a slow first step or a slow second step. So we have a reaction here that we're looking at as an example, and the rate law for this reaction is found experimentally to be the rate is equal to K times NO2 squared. So what we can see from this, first of all, is that obviously this reaction happens in more than one step. Because if this was just a single elementary step, where it was just this collides with this and that's it, then the rate law would be the rate is equal to K times NO2 times CO, and that would be it. So because the rate law is not equal to that, we know that it is happening in multiple steps. We also know that CO is necessary for this reaction to occur, but the rate is not dependent on CO, which means that the CO is not in the rate determining step. Instead, it seems to be that two different NO2 molecules are participating in the rate determining step. And so what we're going to do here is we are going to just make up a reaction mechanism. And this is actually how it's done. This is how chemical kinetics people work all the time. Is they have a balanced chemical equation, they have a rate law, and they just make something up to fit to try and find something that fits both of those. And so if we look at this proposed mechanism, we have a two-step process where the first step is the slow step and the second one is faster. So in this particular reaction, we have an intermediate. If you remember our intermediates from back here, this is a molecule that is created and consumed within the reaction itself. So because it's both created and consumed, it never actually, in a sense, leaves the reaction. And so it's not going to show up in the balanced chemical equation. And as we'll see in just a second, that also means that it can't be in our rate law. But we're not going to have to worry about that in this particular case. So the NO3 is an intermediate, and CO is not involved in the rate determining step. So far, this looks like a good possibility. Actually, I thought we had an extra slide there, but the way that you can see that this particular reaction mechanism makes sense, and we don't know for sure, just from looking at it, that it is the correct rate mechanism. But anytime you are trying to write the rate law for a multi-step process like this, you're just going to look at the slow step and write in the reactants from that slow step, which in this case would just be 2 NO2s, which we could simplify as NO2 squared. So that would be the rate is equal to K, and the reason I put K1 is because each of these steps actually has their own rate constant. So that would be the rate law for that particular mechanism. So this mechanism makes sense with the balanced chemical equation, because if you add these two equations together, it does give you this balanced equation. And it makes sense from the rate law, because if we write the rate law using the rate determining step, we get the true rate law that we found experimentally. Now, this does not guarantee that this reaction mechanism is correct, that it is actually the true reaction mechanism, but it is a good evidence that it is the correct reaction mechanism. So that was a slow initial step. Those are the easier ones. because with a slow initial step, you never have the chance of an intermediate in your rate determining step. Fast initial steps, where the second step is the slow one, are a little more complicated. So we have a example reaction here. We have 2NO plus Br2 goes to 2NOBr. And the rate law for this reaction is found to be this. Now, at first glance, this seems like a termolecular process because it seems like we have 3 different concentration units, which suggests termolecular. But remember, we said termolecular processes are so incredibly rare, we were just going to pretend like they don't exist. And so instead, we are going to think, maybe there's a 2-step process that is a little bit more complicated that will yield this same rate law. And so someone proposes this as a possibility. Now, just to assuage your fears, you will never have to propose a mechanism. You will never have to develop and work out, which one is fast, which one is slow, nothing like that. You will always have mechanisms given to you. You will just analyze the mechanisms. I had to write mechanisms. I had to come up with these proposed mechanisms for one of my classes that I took. It was an entire class on kinetics. That was a graduate level course. You are not in a graduate level chemistry course, so I will not make you develop your own mechanisms. So someone has made this mechanism for us. So it is our job to work out what the rate law would be given this mechanism. So the first thing we're going to look at here is that our rate determining step is this one here. It's the second step. And anytime we know what our rate determining step is, we can write the rate law. So if we write the rate law, it says that the rate is equal to K2 in this case, because this is K1, or sorry, this is K2 here, because it's the second step, times NOBr2 times NO. So that is the rate law for that rate determining step. But if you remember from a few minutes ago, or actually I think from the last video, we are not allowed to have an intermediate in our rate law. Because the intermediates don't show up in the balanced chemical equation, because they're produced and consumed inside of the reaction, they are not allowed in the rate law. The rate law can only be expressed in terms of reactants or products, and usually just reactants. But you are not allowed to have an intermediate in there. So our job is to figure out how can we express the concentration of this intermediate thing that is produced in the first step and then consumed in the second step. How can we express the concentration of that intermediate using the concentrations of other things in the reaction? So a nice big clue here. Step 1 includes forward and reverse reactions. So because the second step is slow, if we go back to our example here, because the second step is slow, the reactants, or the molecules that are produced in the first step, are kind of in a traffic jam, waiting to get through the second step. Now this is where the analogy breaks down. The cars don't normally go backwards. The cars don't. They're not going to go into reverse and go back through Toll Plaza A. I guess if they're waiting there long enough, maybe they'd say, I'll give up, and they'd go, pull a U-ey and drive to the other side of the highway and go home. But all analogies break down eventually. Chemically speaking, if molecules are slowed down and they're waiting and waiting to go through the second step of the reaction, some of them will go back and undergo the reverse reaction, to go back to the initial reactants state. And so that will happen here if this step is slow enough to where we will get an equilibrium built up, where we have an equal number of molecules going forward to create this intermediate, as we have intermediates breaking back down again to go back to reactants. So again, the key point here, anytime the second step is slow, the first step is going to be in equilibrium. We'll have equal numbers of molecules going forward as we have molecules going backward. And this is really, really important. The fact that they are at equilibrium gives us our way of finding the concentrations that we need. So the rate of the overall reaction depends on the slow step. The rate law for that step is this, like we just saw on the previous slide there. Actually, it looks like I got a little bit ahead of myself on that slide, because this is all stuff we talked about before. So now it's getting into, again, the same thing I was saying just a second ago. The intermediate can react in two different ways. It can either react to form the final product, or it can go back to being a reactant. And so for that first step, the rate of the forward reaction and the rate of the reverse reaction are in equilibrium with each other. So because the two rates are equal to each other, the rest of the rate law is also going to be equal to each other. And so if we look at the rate for the forward reaction, it would be this. And the rate for the reverse reaction is this. If you're wondering, where did he get those from? That is just from this here. So in this direction is the forward, so I just took the two reactants from that forward reaction and plugged them in. And then the rate for the reverse reaction, this is my reactant. So the NOBr2 is the reactant, and so that is what I plugged in to the rate law. So that's where we got these. So because the forward and reverse reactions are equal to each other, we can set the rate laws equal to each other. And if we do a little bit of rearranging here, and it truly is just a little bit, I'm just going to divide both sides by k-1, we now have an expression for the concentration of the intermediate that is only in terms of reactants or products. And so this we can plug in to this. So we're just going to take this concentration of the intermediate and insert this for it. And if we do that, we get this. And so because we have three different constants here, we're just going to combine those all into one constant. And we have 2 NOs and Br2. And if you check, that is consistent with what we found experimentally. And so once again, this doesn't prove that this mechanism is correct, but it does show that the mechanism is consistent with what we found experimentally. So these are the two options that you're going to have with reaction mechanisms. So let's go ahead and do a quick example with this. So we have ozone decomposing in this reaction, and the experimentally determined rate law is given right there. It wants us to show that this proposed mechanism is consistent with the observed rate law. So we have someone proposing a slow second step for us. So go ahead and pause the video and see if you can work out this problem and prove that this proposed mechanism does match the observed rate law. So pause the video now. Alright, I hope you gave that problem a try. Let's work through it real quick here. So once again, we know we're just going to take the slow step and write out the rate law for that slow step. And that is, and again, doing that is just taking the reactants and plugging them in. This is the correct rate law, but we are not allowed to have monatomic oxygen here. So that single O is not allowed because it is an intermediate. It is produced in the first step and then consumed in this second step. So we are going to need to do the same thing we did in the last example. We're going to take this first step, set the two reactions, the forward and the reverse reaction, equal to each other, and solve for the concentration of O. So for the forward reaction, we have the concentration, well, let's do K first, I guess. So K1 times the concentration of O3 is equal to the reverse rate, which is K minus 1, times the concentration of O2 times the concentration of O. So again, this is the forward reaction, this is the reverse reaction. They are equal and opposite. If we want to get just the concentration of O, we'll divide both sides by K minus 1 and O2. So that will cancel out all of that, and we'll be left with the concentration of O is equal to K1O3 over K minus 1O2. And so this we can plug in here, and that will give us the rate is equal to K2 times K1 over K minus 1, and all of that will just be one new K. Times O3 times O3 over O2. And so this can be simplified as O3 squared, and actually you don't even need to do it over something, because O2 raised to the negative 1 is 1 over O2. So this does indeed match the experimentally observed rate law. Alright, I hope that made sense to you all. I know this video's gone on kind of long, but this last little thing here is really short, and I don't want to have just a 3-minute video at the end here, so just let me very briefly talk about catalysis. This is an idea that is pretty well known in modern day culture, the idea of having a catalyst, but most people kind of think of a catalyst as just something that helps you move forward. Like if you have a catalyst in your life, maybe it's someone you care about, and like, oh, they're my catalyst, they help me do things, they help me go. Or maybe you think coffee is your catalyst. But chemically speaking, catalyst is it has a very specific definition. A catalyst is something that assists the reaction. It helps it go faster. It increases the rate of a reaction by lowering the energy of activation by offering an alternate reaction pathway. So it offers a different reaction mechanism that lowers the energy of activation, and it's not consumed. And that is the really important thing, because there's plenty of alternative reactions that are lower in energy than other reactions, but they're not considered catalyzed reactions because everything is used up. A catalyst is special because it helps the reaction go, and then it gets spat back out at the end. You don't lose the catalyst. Now, these can be either heterogeneous or homogeneous. If a catalyst is homogeneous, that means that it's in the same phase as the reactants. So if you have a gas that helps another gas react, that would be homogeneous. But they can also be heterogeneous. So the catalytic converter on your car, that is a heterogeneous catalyst because it is a metal. And the thing that is helping catalyze is a gas. that flows over it. So you have a solid and a gas, different phases, so it is heterogeneous. So this is analogous to trying to push a rock up to the top of a hill so that you can roll it down the other side. And then a friend of yours comes by and says, yo, dude, you don't need to push it to the top of the hill. You just push it over the side of the hill. It's fine. Your goal is just to get down here. And so you're providing an alternate pathway where you don't have to push it all the way up. There's an easier way where you don't have to go quite as high. So usually catalyzed reactions, even though they are lower in energy of activation, they are also usually more complex, but that's fine. The chemical reaction doesn't care how many steps there are. All it cares about is what is the maximum energy that you need to get to. And so if that maximum energy is lowered in the catalyzed reaction, that means that the reaction is going to go faster, because there are more molecules that can get to this energy state than there are molecules that can get to this one. So it'll be faster with this catalyzed version. Oh yes, so last little thing here. The enzymes in your body are also technically considered catalysts because they are not consumed. And these are a special kind of catalyst called lock and key, because they actually work on what is essentially a size exclusion or shape exclusion principle, where they will react with essentially anything that they can get their hands on, but they can only fit very certain shapes. So only molecules with a certain shape can fit into the enzyme to be reacted with. All right. Phew. So that is the end of this chapter. Good luck with the homework on this one. If you have any questions, feel free to email me or talk to me if you see me in class. And I will talk to you all in the next video, which is going to be over equilibria.